What we're going to do today is to talk about this new MacFlow algorithm that is super new, like this year. And yeah, it's exact and it has n² running time, so not optimal in sparse graph, but optimal in dense graph. Okay, and the key idea, like today is about I try to highlight the key structure like in this algorithm, which is something that we call shortcut, and it is based on SE hierarchy in directed graph that we learned last time. Okay. So you're gonna see what this thing is and how come it's useful for exact MacFlow. And later class, we're gonna see how to, you see that, we basically get exact MacFlow in n² time, but with some assumption. We're gonna remove this assumption later, in later lectures. Okay. Let me recap first. Okay, so good. The key object that we're going to use today is SE hierarchy. So in directed graph, the SE hierarchy is, you can think of it as a partition of edges, right? Such that, into level, from 0 to L, and for each level I, EI is expanding in G after removing all edges from level above. Okay. For example, here, I can say that E3, the green thing, is expanding in the whole graph. And the red edges, E2, is expanding after I remove E3. So after removing E3, you get the red components, and E2 is expanding inside the red component, in each red component, and so on. Okay. E1 is expanding inside each blue component after removing E2 and E3. Okay. Just the same concept, but in undirected graph, that is this kind of picture in directed case. Okay. E0 is like a DAG edges, so each connected component in after removing all the color edges is just singleton. So the black graph form a DAG, and that's the expander. So E0 is expanding in E0, which is G minus. Yeah. Okay. And also this hierarchical structure also induces a vertex order, which we call tau. This vertex order tau is just such that will be such that for every cluster, this tau, tau map a cluster to a consecutive interval. For example, every node in this cluster, in this red cluster, is mapped to this interval. Okay? So this is I put the number 1, 2, 3 up to n here. Okay. So when you have the SE hierarchy, it justifies a vertex order. So this is just from last time. A question about this? Okay. Good. And so now the key object is a shortcut. Okay? And what we're going to do is to define a shortcut graph. And the idea is this. The idea is we're going to add stars. You have the directed graph, and I just kind of add a bunch of stars to this directed graph. Where do I add a star? I add it on the expanding set from the hierarchy. We see how it is. precisely. And not just adding star, I also gonna set the edge weight. Like in the beginning, there is no edge weights. This is like a graph for computing flow. So there is just capacity. There is no weights. And then I just gonna assign some edge weights. Yeah.
Wait, so sorry. The like out neighbors of the center of each star is like one cluster in the graph or in the SE hierarchy.
Something like that. We're gonna see it precisely very soon. Yeah. Basically, yeah. For now, just for each cluster, I add one star. To where is the leaf of the star is basically on the expanding set of edges. But yeah, we'll see this. Yeah. Okay, so I'm gonna add star and then I'm gonna set edge weights appropriately. So, but that's the plan. But like, in the beginning, let me just warm up for you, just to analyze when we add a single star, and then analyze what's good about it. Okay, and after that, once we understand this one, I'm gonna tell you the full construction, and then we analyze the full construction. Okay. So let's warm up by looking at one single star on an expanding set. Okay. So what I mean is here. Suppose that I have a node weighting. Wait, one second. Oh, wait. Oops. Okay. Suppose that I have a node weighting A, okay? Like this picture, this point, node weighting A, and then a star TA, a star on A with capacity scale kappa is like this. I'm just gonna add first like a one dummy node. Like that's not original from the graph, just one new node. Okay? This root R. And then for every node on the subport of A, we just connect it to the root. And the capacity of this edge, this one, for example, is going to be kappa times the A of V. For each node V, just put this capacity to be kappa times A of V. Okay. So this capacity scale is this capacity scale here. So that's how we add a star on A. Okay. And okay, that's the construction. Okay. And now here is the setting that we will consider. Suppose that this A is expanding. Okay. Which is the case, like we're gonna only add a star on expanding set. Okay. So suppose A is expanding, and then let's look at the graph. I call it shortcut graph, where I just have a graph and then I add a star. And let's set the capacity scale to be epsilon phi. When this this is phi expanding, and then I set the capacity scale to be less than phi. Okay. The claim is this. The claim is that when you look at any degree respecting demand, okay, if this demand is routable in the shortcut graph, then it's still routable in the graph with with congestion that doesn't increase that much. So first note that when you have a graph and you add a star, it only increase routability, right? It's just like your routability only increase. You just add a star. But here it says that it doesn't increase a lot. Whatever you can route in the shortcut graph, you can still route in the graph with basically the same congestion. That's what it says. Okay. So let's see. This is a statement. Okay, let's see the proof. Okay, so let's say that like I have some flow that routes some demand D. This flow is in shortcut graph. Yeah. Now I need to construct another flow that routes the same demand with congestion that like 1 plus epsilon. And this like with congestion 1. Yeah. Okay, so let's say that this is flow F. Okay. And this flow, some flow path don't use the star edge. Some flow path might go through star. So what we need to do is just to forbid it from using the star. Okay. Okay, so let's look at the flow path that go through star, right? Like there are this one go like this and this one that goes like this. Basically, this will induce like just by inspecting the flow path going through the star, it induces the demand between like on A, right? It says that suppose that I want to forbid using this thing, it just means that I just kind of need to route from here to here and from here to here. Okay. What is this demand? Let's call it dA. Now dA here will respect epsilon phi A. Why is that? Why this dA would respect epsilon phi A? What's the capacity of this guy? It's just epsilon phi. If this is V, this is AV. If this is U, this is epsilon phi AU. Right? So like the total flow that goes through the star edges respect epsilon phi A. Like for every star edges that you go through, just respect epsilon phi A. There can be another flow path too, like maybe like another flow path here that use this thing again. But in total it's just use at most epsilon phi A. Okay. So when you just because of this, like when you look at the flow path that goes through the star, it will just induce the demand that respect epsilon phi A. Make sense? Okay. Now, how this demand respect epsilon phi A, but A is phi expanding. So how like what's the congestion that you can route? Like so dA is routable with congestion what? Yeah.
1 over phi.
1 over phi. Not quite. If it just respect A, then
okay.
it would be times this thing. Right? If it just respect A, it would be routable with 1 over phi congestion. But then like it actually respect, it's much smaller. It respect epsilon phi A. So actually it's routable with congestion epsilon. Okay, so let's say that, yeah, so if A is expanding, there exists a flow that routes this demand. Let's call this FA, that routes this demand with congestion epsilon. So now, okay, we now basically can route it. Okay. We just remove the star, look at the demand that this induce, and then just route this demand using the using like route this demand between A. This thing will have congestion epsilon. The original flow have congestion 1. So you might kind of add them together, like they can use the same edges, but the total congestion is just 1 plus epsilon. So again, like basically we can forbid F from using the star edges just by removing the thing on the star, and then just reconnect the flow path using the flow between A. This guy have congestion 1, this guy have congestion epsilon, so you get a flow routing the same demand with congestion 1 plus epsilon. So that's just like, okay, so the point that I want to make is that if you have some expanding set and you add a star on top of it, it doesn't really change things much, right? Like if you have a graph, you have some A that is expanding, so it means like the connection between them is already good. If I add some star with like small capacity, that doesn't increase the connectivity between them too much, then it doesn't really increase anything. Okay. So adding a small capacity star on expanding set doesn't change routability too much. And in our, yeah.
I guess this is because we can like route some demand between the endpoint, the leaves of the star.
Yeah.
Is that what we do, basically?
Yeah. Like we know that A was expanding, so any point in A could be routed using original graph anyway. Now, okay, we add like some shortcut. You can use this thing, but it's small. It doesn't really help. Okay. Good. Okay, now, so yeah, the point you just need to remember now is just like, if you have a flow on the shortcut graph, I can kind of project it back to original graph with like and the congestion doesn't really increase. Okay. Like I can basically forbid using the star and increase the congestion by a bit. Okay, so keep this in mind. Now the full construction is like this. Okay. Suppose that we have this hierarchy. Okay. There's gonna be like a bunch of clusters. Okay. Let's look at like a level, like a one level, like one cluster at level I. Okay. So maybe, do I have picture? Maybe I have one. I add this picture first. Let's say this is H. There are like many other things outside, right? And what we have is like, okay, there is gonna be like a lot of dark edges, but there's gonna be some edge here at level I, some edge at level I here. Okay. So this edge is gonna be expanding. The edge here is expanding in H. Okay. The separator of H will be expanding in H. Okay. So what we're gonna do is like we're gonna consider the star on the endpoint of this edge, and we set the capacity scale to be like epsilon phi over L. So maybe like think like I just add, like I look at the star. This is the star. Okay. That's a star for the cluster H. So for each cluster, there is like an endpoint, there is an edge set for that level that is expanding in H add a star where the endpoint is the endpoint of this expanding edge. Okay. What's the capacity? Well, the capacity is like if this edge has capacity CE, then the capacity of this guy will have capacity CE times, phi over L, epsilon phi over L. Okay. So if this capacity is 10, then this guy will have phi times 10.
What if there's a vertex with multiple edges in the?
Say it again.
What if there's some endpoint with multiple edges in the separator? Like which?
Right. Then like think like you add like for every edge you just do this,
So,
and if there are many, like if it has many edges, then like the capacity here add up. Or you can think like is there are parallel edges, but you can just merge them.
This may be a stupid question,
No.
but does this work only in directed graphs? Because the hierarchy has to be directed for this too. How do we construct this hierarchy in undirected graphs? Because you're looking at backward edges here, right? So.
Oh, for the undirected graph, like the separator would be just all edges crossing the component, the children component.
Okay.
It's just now like in the directed graph there are like a forward one, and we only consider backward one.
Okay.
Yeah. So separator in a related graph is just all separator. Here is just only backward separator.
But will the algorithm still work with it?
Let's see. It will just work because directed graph is just generalization of undirected graph.
Okay.
Yeah. Okay. Good. So now what we're going to do is just, you have a graph, I add a star for every cluster. So like I have this hierarchy. Okay, I look at this cluster, I add a star for this cluster. Have this cluster, I add a star for like the star that connect to the endpoint of the red edges. And same here. And there is a green star too, which is just for the whole graph. And it connects to the endpoint of all the green edges. Just add a star like this for every cluster. Okay. So that basically determines edge capacity of every edge. The original edges have just the same capacity. The star edges has capacity like I described. So now I just need to tell you what is the edge weight. It's going to be weight too, not just capacity. And the edge weight is like this. If the edge is from original edge, from the graph G, then I just say that the weight is just the difference between tau. We have seen this several times now. We will use it again. This is like the kind of the key to get n square in many other previous algorithms. It's just the same thing here. Okay. And okay, so for example, if this is like a u and v, then the weight here is just tau u minus tau v. Okay. And then if it's a star edge, if it's a star for like cluster H, then the weight is just like basically the size of the star. the size of its cluster. For example, this one have like 6 nodes. So the weight of every guy here is 6. Okay, that's the construction. Okay, so that's it. Now we analyze it. Okay. So the first thing I want to analyze is just kind of similar to what we have done. That is, I want to say that first, all these stars that we add, in total don't really change, don't really increase connectivity of the whole graph. So I want to say that first we're going to show that for any flow on the shortcut graph, okay, given the flow on the shortcut graph, you can kind of project it down to original graph, so that it doesn't really increase the congestion. So we can forbid using the star. Okay, so what I mean is, given the demand D, if D is routable in the shortcut graph, then it's still routable in G with congestion 1 plus epsilon. Okay. And the idea here, you see, it should be quite similar. We used to just say given 1 star, we can forbid using it if the capacity scale of that star is small. Okay. And actually, if I have many stars, but suppose that all the stars are disjoint, and the capacity scale is a 1 over phi. Okay. The proof that we just saw, you can just forbid all of them too, simultaneously. And the capacity, the congestion would increase in total, still epsilon, although we forbid many disjoint stars. Okay. But now, okay, all the stars that we add, they might not be disjoint. But they are just L many levels. They are log n many levels. So they are a collection of disjoint stars. Just log n many of them. So that's why I just set the capacity scale to be epsilon phi over L. So when we remove all the stars from one level, it just increase the congestion by by epsilon over L, and do this for L many levels. So in total, the congestion will increase by epsilon. Make sense? Okay. So yeah, I will not go over this. Okay. Question about this? Good or not? Okay. All right. Next is, I'm gonna say that the weight that we assign is quite big. Okay. Big in what sense? So, wait. Yeah, the weight that we assign are quite big because suppose, for example, that if the edge weights are just unit, suppose that I just put 1 unit of weight on every node, on every edge, then this sum this is just 1, and so the total weight would be at least this sum would be at least m. Okay. But I'm gonna actually say that our edge weights are actually big in the sense that this sum instead of m is just a log n. So it's less than m. That can happen when the edge is the weights are big enough. So it's big in this sense. And that is kind of not too hard to show. Like we have seen this for some time. Like there are two types of edges, the original one and the star edges. For the original one, well, like if I look at this sum, like I just look at this sum, summing over all original edges. This is just the same, by definition, it's just this. But we have seen that like if I look at the node U and I just sum up the contribution of this thing incident to U, this sum is just going to be like this thing will contribute like 1, this thing contribute 1/2, this thing contribute 1/3. So this sum is just at most like the sum from like the harmonic sum for each node U. So this in total is just n log n. Okay. And for the star edges, that's also quite easy. Like for each cluster H, right? For each cluster H, I have a star. Okay. So now like there are like for each star, the weights here is like the size of the cluster. So each of this is just 1 over the number of nodes in the cluster times the number of edges in the star. The number of edges in star is just at most the number of nodes in the cluster. So this is at most 1. So for each star, this total contribution is just at most 1. How many stars are there? How many clusters are there?
Log n.
Can be more than that. Like there can be like disjoint star like this. There can be many star like this. But how many are them?
Can we just like round this with n log n again because there can't be more than n per level?
Yeah, there cannot be more than n per level. You can say a bit like so it's at most n log n, but you can actually say that it's at most 2n. Just because like it's like you have, yeah, it's like a tree, right? A tree with n leaf can have at most 2n nodes. Okay. So actually like this contribute in total like 2n. Like this is n log n, this is 2n. So in total this is like n log n. Okay. So the weights are big in this sense. Okay, now here is the core part. Okay. So what I say is that previously I just showed that like the weights are large. But now here's the like core part. We're gonna say that given any flow in original graph, we kind of always can lift it to the shortcut graph so that you get a flow that is short and have like congestion the same congestion. Doesn't increase congestion. Okay. So our weights are like if I assign weights to be all 0, like getting short flow would be trivial. But I just say that okay, the weights are actually large, but I can still show how, like given some flow that is long in original graph, I can lift it to like to shortcut graph, and it's actually short now, although the weights are large. Okay, so let me formalize this. Suppose that our edge length are this weight function, weight W. Okay. We say that the flow have maximum W length, D, if when you if every flow path have W length at most D. So, okay, you have a flow, which is just like collection of paths, right? And then look at this path. Now, like this guy have the total weight at most D for all paths in the flow. So that's maximum W length. And what we're gonna show is that for any demand, that is like kind of on original graph, so it respects the degree. If it's routable in G, it's also routable in H, in shortcut graph. But now the length is just something like N. So you should think like this L is going to be log N, phi is going to be like 1 over polylog. Epsilon is like, think of it as like small constant. So this is just order N. Okay. Note that this is not clear because, I mean, if a graph is a DAG, that would be clear. Because, okay, we assign the weights so that like for node U to V, okay, this is like the weight is like the total increase in the order, in the topological ordering. And the topological ordering just can only increase from 1 to N. So if the graph is a DAG, if G is a DAG, you don't need to use shortcut at all. And the weight, the length here, the length of the flow would be just N. Maximum length is just N. But if the graph is not a DAG, it's not clear at all. Like the flow can be actually long. Why? Because there could be a flow path that first kind of go in, like increase in the topological order, and then it use some backward edge, and then okay, it goes here, almost reach T, but no, I just gonna go back, and then oh, yeah. Just keep doing this until, so it can be really long. Right? So okay, when the graph is not a DAG, you don't always proceed in the order. You might go back, and that can be long. But now we're gonna say that, okay, if you have some flow on G that is long, actually I can try to shortcut it using some star and make it not too long, almost like in a DAG. Okay, that's what statement this statement is about. Okay. Yeah. If DAG clear, but G is not DAG. So this is non-trivial. Okay. So what we need to do is like, suppose that I have some flow in the original graph that can be long. What we're going to do is like kind of try to shortcut this flow path by path. I just gonna look at, let's say this is like a flow. Actually, let's say it route. Yeah. So let's look at one path, and let's say that this path it starts from S and end at T. Okay, and let's say that this path have value but val. So I have some flow. There are many paths. Let's say that I look at one path P from S to T. This path can be long, what we're gonna do is like we're gonna construct another flow for this path P. That route the same thing from S from it path P route from S to T. I'm just gonna route the same thing from S to T with the same value. But now I said that this flow will have maximum length, like something like n. Okay, and then my resulting flow at the end, f prime, is just a flow on the shortcut graph. And then I just sum, which is just collect all this flow fp from every, like summing over all paths, summing over all flow paths of the original flow. Okay. That's the strategy. If I can do this, like for every path that can be long, I can shortcut it to be fp, that is short, and then summing over all of them. The total, the maximum length of f prime here would be like something like n. Okay. So what I need to do is like to kind of show you that how to construct from path p to this flow fp. And when I sum them up, sum this thing up, then the congestion don't increase. Okay, that's our plan. Okay. Okay, let me tell you how to build FP from a flow path P. Okay, we're gonna kind of proceed top down. As in, yeah, like I have a graph, and then I have like some cluster and another like cluster. And the flow path can look like, yeah. And we get this path is like some crazy path. And what we're gonna do is kind of modify this path top down by consider the top cluster first and then modify it. Once you're done, then modify it according to like the lower level cluster until you're done. Okay. So let's say that now we are at like cluster H. Okay. We have modified so far, and now we are at cluster H. And let's recall that the separator of H is just a set of backward edges crossing the children like this. Like H is just some cluster, and there are like children, and there are like the separator of H is backward edges that cross the children, like that cross the children cluster. Okay. And this thing will be expanding, right? By definition, this is like phi expanding in H. Okay. So now the idea is this. Every time that P goes through the separator, like the red edges, we're gonna try to leak some unit of flow through the star. Okay. Like we don't want the path to use many separator edges. Why? Because you see, like the only reason that the path can be long, as I mentioned, is because they use backward edges so that it proceeds forward and then go backward. Like we don't want that to happen too many times. So I want to forbid the path from using separator of H many times. And the idea is this. Let's say this is a path P. Okay. And it kind of goes through the separator of H many times like this. Okay. Now, let's say that like I look at the first 1 over epsilon phi edges from the separator of H. This is the first. Let's say this number is 2 for simplicity. Look at this first, 1 over epsilon phi edges from the separator, and the last 2 here. And what we're going to do is just when you go through the separator edge, what I'm going to do is just this path have value wow, right? I'm just going to leak epsilon phi wow through the star edge and then go here. Okay, so it kind of help you, it kind of shortcut some unit of flow through the star. And then, okay, go through another one, it shortcut again. So it kind of leak the flow through the star. How many times this can happen? Only 1 over phi epsilon. If this happen more than 1 over phi epsilon, you have leaked all of them. Then like this is now empty flow. You leak all of them. You see, like, so now this is just force you to not use too many separator edges. So this is like the important picture. Question about how we modify this. This is the key. Okay. So you see that just by doing this, our flow will contain at most 2 over epsilon phi edges from the separator. And also from the star. Okay. By the way, I want to note that like the path actually can go in and out of the cluster many times. It's not like that I have one cluster H and then I have path that looks like this, and then we kind of shortcut. And what we do is like we kind of shortcut it. The path can be even more crazier, right? It can be like like it can go in and out of the cluster many times. Point is just that it really doesn't matter to the argument. I just say that okay, whenever it goes through the separator edge, I just link it to star. And no matter what, it will just use at most this many edges from the separator. Okay, good. So that's the construction of FP. Now we just need to analyze it. So first, let's talk about the congestion. That's kind of easy part. Okay. So you see that every time that I kind of make a leaking operation, it only reduces the flow value on every edge, on every original edges. I only increase the flow value on the star. So the congestion on the original edges will remain 1. We don't need to care about that. Just need to analyze the congestion on the star edges. Okay. And now let's say that I consider one star edge. Let's say that like this is like some separator H. This is H is in separator of H. Okay. And let's say I look at the star edge here. E prime. Okay. What's the total? I just need to count what's the total flow that goes through E prime. Okay. But we know that like, okay, when there is a flow of value val, I just kind of use val times epsilon phi here. Actually like over L too. Yeah, I forget that. Yeah. Right. But the total, and there's going to be maybe another flow. Another flow with val prime. Then we're going to lead to the star again. But the total flow here, the total flow that goes through E is just at most like the capacity. Maybe I should write this actually. This is at most the capacity of E. So this total flow going through E is at most capacity of E. What's the capacity of E prime? Well, we set it to be like capacity of E prime is literally just this thing, capacity of E.
Where does the L come in here? Because I thought we were just routing like epsilon the flow earlier.
Good. Epsilon, this thing, let's see.
Like I understand that's the capacity.
Okay, maybe I should put 1 over 5 over L all to all of this actually. Yeah. Right. Yeah, because let's put L to everywhere. Yeah, I forget that. Right. Good point. Yeah. But anyway, like you see now that like this sum is just at most epsilon phi over L times capacity, which this thing itself is the capacity of E prime, because that's our capacity scale. This is our capacity scale. So it means that the congestion is at most 1. Congestion on this guy is at most 1. So every star edge has congestion at most 1. So we are done. So now what we are left with is just bounding the length, maximum length of f prime. How to do that? Well, it's just enough to bound the length of fp inside f prime, because f prime is just a sum of fp. Well, there are like several types of edges. First, let's look at fp. Look at the star edges in fp. Let's look at each cluster, right? The total length of star edges in fp, it's just at most. This is the length of star edges in H, and the number of a number of edges that we can use. Okay, and then we sum over all cluster. And now, okay, the total size of the cluster in total, this is at most NL. Right? This sum is at most NL. So you get that this is like NL square, yeah, over epsilon phi. Okay. Okay. That's the total length of star edges. Questions? It's gonna be the same for backward edges actually, because let's look at each cluster. The total length of edges in separator of H in FP. separator of H, which is like a backward edges crossing the children of H. This is just like at most, yeah, I forget all the L here. L square. Yeah. At most this many edges. Each of these backward edges have length trivially at most the number of nodes in the cluster. Because, yeah, like the weight is just the distance between, like the difference between the order tau, but this is just inside the same interval of this length. So this is the same kind of thing, the same bound there. So summing here is just the same here. Yeah.
Why is the length v of size of v of h?
Oh, yeah, like this is like you just get that like this is h, right?
Yep.
And then like the weights here, like all the nodes in h kind of map to interval of length of size of this size.
Oh, I see.
So like any edge within this interval could have the difference here at most the size of the interval.
Oh.
Okay, good. Now we need to talk about the forward edges. Okay. And here it helps to actually, yeah. Anyone have ideas how to bound this actually? If I don't use backward edges at all, what's the length? What's the total length here?
N.
At most n. It just can only go forward. Okay. But now I might use backward edge. I might go forward. And then maybe like there's some backward edge here. And then I will go forward again. And then I might need to use backward edge. And then I go forward. What do you think should be the length of the forward edges in total?
Is n plus like the length of backward edges?
Exactly.
Like how much we go back?
Yeah. Yeah. Like, okay, in the first time that we go forward, is that as much n? But like, only reason that we can go forward again is because of backward guys. So we can basically charge this thing to the backward one. Okay. So yeah, so that means the length of forward edges is just at most n plus the total length of backward edges. Yeah. So that's basically of the same order here. So we get that the total length here is at most nl square over phi over like epsilon phi. Okay, so let me conclude about this core structure. Yeah. Given, suppose that I have a hierarchy with L levels and some parameter epsilon, we can build a shortcut graph of a graph such that the weights are quite large. And for any demand, you can first lift it up to short flow. Like if it's routable in G, you can lift it up to shortcut graph such that the length is small, like something like n. You can lift it up to short flow. And given anything on the shortcut graph, you can project it down without increasing capacity congestion by much. This is like a key structure that you should have in mind. Okay, it's quite cool. Yeah. Okay. The remaining components are more algorithmic. Okay. So let me tell you how this is useful algorithmically. Okay. And the reason it's useful is because weighted push level run fast in this shortcut graph. And the intuitive reason is this. Actually, let me tell you first. We know that now, like, when you look at the shortcut graph, you only kind of need to care about short flow, right? Because when you if the max flow in original graph have value 10, there is going to be flow of value 10 in the shortcut graph too, but that's short. Okay. And the thing is that push the level, you have seen once that if you just want to find flow that is competitive to short flow, then you can compute that fast. We basically use that. Okay, so what I mean is here, we can solve this. We have an algorithm, short flow, such that given the input with some weight here, and parameter d and epsilon, okay, it basically, given g, d, and epsilon, it returns a flow, such that it is as good as a short flow. So our flow here will be as big as f star, but f star, where f star is the maximum flow, such that the average length in W is at most D. So it's competitive to flow of length D. And the running time is going to be something like this. So something like sum over this 1 over weight. And you can forget log n. So this is something like the sum over weights, basically. If you forget about epsilon and log n, that's basically kind of running time. I mean, we have seen this before when W is all 1. Actually, we proved this. You can have a look in previous, some lectures ago. We saw the specialized version of this theorem when the weights are all 1. That is, F just have normal average length at most D, which is the number of edges on average, the number of edges on the flow path on average is D. And the running time was something like MD over epsilon. We kind of spend time per edge, D over epsilon times. But now, okay, we have this D over epsilon as well, this D over epsilon. But here we have edge weight. But you remember the point in introducing edge weight to push the level is that if the weight is large, we don't need to probe them many times. So the weight that we the time that we spend on each edge is something like 1 over W of that, 1 over weight of that edge. So this is can be less than M, like today, can be N. Okay, I might just talk about this tomorrow, how to do it, or it might be in homework. I'm still not sure, but okay. Anyway, this is but this one is the algorithm that, if you remember, is the one that set the weight on original edge to be 1 and the weight on backward edges to be 0, and that works. We can make it work for the case when this is not just all 1 too. Okay. So it's kind of believable that you can do it. We will try to do it in this course too. Okay. Anyway, let's see that if you can do this, then why are we good? Okay. Like we can compute flow that is competitive to short flow, and the running time is something like this sum. Okay. So now let's see how to get max flow. Okay. Let's say that you have a graph with edge capacity, like integer edge capacity, let's say at most poly n. And there is source and sink, S and T. And you just want to compute ST max flow. Okay, so here is the exact maximum flow. But one thing to note is that you can actually reduce the problem to approximate one. Why? Yeah, this fact is that like we can compute maximum flow just by making like something like log many calls to approximate, like even like as bad as like a 1% approximation. Like if you have 1% approximate maximum flow, then you can just solve exact one. Why is that? This is like a kind of standard thing that I'm just gonna go quickly. Just repeatedly compute maximum flow in residual graph. Okay. In each round, you get the flow. The flow is like 1% big, so it will reduce the maximum flow size in residual, like the size of maximum flow in residual graph will be smaller by like 1%. Like you reduce it to 99%. Now, like how many times you can reduce this, right? The original max flow value is like at most, if I be super generous, like it's at most m times c. So like after k many calls, where k is like log n, the maximum flow value would drop to like this thing to the k times the original number size of max flow or like initial max flow. Thus, if k is big enough, like log n, this is like less than 1. So you can just kind of keep like the exponential value of max flow keep reducing. Sorry, the max flow value in residual graph keep exponentially reduce. After log n times, this is less than 1. If it's less than 1, actually it must be 0. Why? Because actually we can assume that, yeah, actually max flow value must be 0 if it's less than 1, because we can assume that the flow are integral. Why is that? Well, even though, like this is non-trivial, by the way. Like even though, suppose that your flow is not integral, like suppose that your algorithm, even if your graph has integral capacity, your algorithm might not give you integral flow. But there is some black box algorithm that allow you to just route the flow to make it integral in m log n time. Can do this in m log n time. I will add citation to this soon. Yeah, it just use some simple link cut tree. Just yeah, some. It's non-trivial, but like once you see how to do it, it's simple. But yeah, but the point is you can always assume that your algorithm return integral max flow, integral flow. So if this is less than 1, then you can. This is actually 0. Okay. So once it's 0, it means that your flow is already maximum. So okay. Anyway, now it means that the goal here is just to compute approximate max flow. Just want to note one thing quickly. This reduction only works if you have approximate algorithm for directed graph. Right? Because if the graph is like when you look at residual graph, the residual graph become directed immediately. So you need approximate algorithm on directed graph to work on top of residual graph. this reduction from exact to approximate doesn't work for undirected graph. Okay, so now let me tell you approximation algorithm. Here's the idea. It's just put everything that we saw together now. Like suppose that you have G, and let's say that like F star G is like a maximum flow that we don't know. First, compute SE hierarchy. Given this SE hierarchy, compute a shortcut graph. Okay. With like this capacity scale, something like epsilon phi over L, and this epsilon, let's say, is even 1. I don't really need to care much about epsilon here. And by the fact that this shortcut graph have this lifting property, I know that there exists, not max flow, there exists ST flow in the shortcut graph that route the same value as maximum flow. It route the same demand, but now it's short. Right? I can lift any flow in original graph to short flow in shortcut graph. So now this is like a kind of our target that we don't know, but we know that it exists. There exists short flow in shortcut graph that whose value is as big as maximum flow. So now we just use short flow algorithm that I just said, right? Just run short flow algorithm on the shortcut graph, when and I want to compete with the flow with this length d, which is something like n. And let's say I just want some approximation, like this approximation, I just want maybe like even half. I don't care too much. And let's say now I get this flow on shortcut graph. So this flow will have value as big as like f star h. Because like I said epsilon here to be 1/2, so this is like this thing over 2, which is as big as the original value of max flow over 2. But you see the running time is something like this sum times d. D is like n. This sum, we also know that this sum is something like n log n. Right? So this is basically, actually, sorry. Yeah, this sum is something like d log n, n log n. Yeah. So this is basically n squared. So you see, like, this is the point where the running time is fast. We need like this weighted push level, and we compete with a flow of length n. So the running time is n log, like n squared. Now this is the flow in the shortcut graph. We know that there is another flow. Like we can project this flow back to the original graph. But by the projection property of G, of our shortcut graph, we know that when we project it down, the congestion don't increase too much. Right? So F would route the same value with congestion, 1 plus epsilon of like epsilon, like this epsilon of the shortcut, the hierarchy. That's like I set this to be 1, so this is just 2. So then I can return this thing. Why? Because like this thing, this FG has congestion too. So this now is like has no congestion. It's feasible. Okay. So now you see that like this flow is not integral, right? I actually scale it down. I can make it integral again using this black box that I mentioned. Anyway, how big is this one? Well, it's as big as it route like FG would be as big as like max flow over 2. So this is as big as max flow over 4. So this is actually like 1 over 4 of approximate max flow. So to conclude, this basically kind of give approximate max flow in n square time. And it just implies exact max flow by the reduction I made. We just saw. Yeah.
Wait, sorry, could you scroll back up to the reduction real quick?
Yep.
So in the first part, it says that in each round the max flow value reduces by 1 minus 1 over 100. Wouldn't this like indicate that, maybe I'm misunderstanding this, but that, like you would need to call max flow a smaller number of times if you had like a worse approximation?
Yeah.
Yeah.
Like but it's still small, right? Yeah. Like
Right.
if this is like 1 over log, then the number like this would reduce by 1 over log. So this would be, instead of log n, it would be log square, for example.
Right.
Yeah.
I guess, okay, but then like the approximate max flow algorithm, is the runtime for that dependent on like what you set epsilon to be? Or sorry, what you set the like 1 over 100 to be? I guess I'm just like, I don't know, it seems like why would you choose to have like a 1 over 100 approximation?
Oh, this is
Like,
like
okay.
this is like arbitrary.
Okay,
Yeah.
okay,
Like
gotcha.
it's just some number. Like this can be like totally like anything. Like 1 over 4, 1 over like polylog. It would change. It only affect the running time.
Right.
Yeah.
Yeah. Okay, but like if you got a worse approximation, then you would get a better running time, is I guess. So, but then it would, yeah, okay.
So basically, like the approach here will not give you so like I don't know how to make it faster if I want worse running time. Sorry, I don't know how to make it faster if I want worse approximation. Like here I get like something like 1 over 4 approximation.
Mhm.
If I want, let's say like 1 over log n, I don't know how to make it faster.
Oh, okay. Yeah. Gotcha.
Okay.
Like, I guess I'm thinking, in a sense, you want a worse approximation, right? Because then you need to.
I only need a worse approximation.
Right. Okay.
Yeah.
Gotcha.
Good. More questions?
You scroll up. Yeah, what happens if C is not poly n? What do we do?
Then like this doesn't work. Yeah, like most of the time people just write like when like the running time should be written like n square log c, like to be more precise. This is when like this is usually the running time that people say is weakly polynomial, and because it has this log c dependency. If you want like c, if you assume that c can be exponentially big, then like no one knows how to beat mn yet actually. Yeah. But I don't know, like assuming that the capacity is exponentially big, sometimes I don't find that so natural because just to store the number, you need like a lot of bits already. Yeah. Okay. So we cheated. We cheated in some place. Can you spot? Yeah.
Do we know fast SE hierarchy yet?
Yeah, exactly. We don't know how to do this fast. Okay. There is another place that we cheated. There are 2 places.
Can you like not know what weights to put on the, actually,
No, that's fixed. Yeah. Let me tell you because it's here. I just said that okay, given flow in the shortcut graph, there exists another flow in original graph that route the same thing with not much more congestion. I didn't say to you how to find that. Right. So this is like two things. We need fast construction for constructing SC hierarchy. We didn't learn how to do that fast yet. Next is that we need a fast projection. Given a flow in shortcut graph, actually I need to tell you how to compute, how to project this down to flow in G with low congestion. Okay, so yeah, we just showed that it exists, but we need algorithmic way to do it. Okay. So now the solution to both of this will basically use MaxFlow today. So this is the kind of chicken and egg situation. We need to use MaxFlow that we built today to solve this thing. We use this thing to build MaxFlow. And the point that I need to tell you is like how to overcome this. Okay. This is now like about algorithmic way to like overcome this whole thing. But the key idea, the key structure is this shortcut graph. Okay. So what I'm gonna do tomorrow is first like tell you how, at least in principle, that why you think you can do this, both of this. Okay. And yeah, and like we're gonna see like how in principle you should hope for like a fast construction of SC hierarchy and fast projection. And then we see how to really solve it next week. Next week. Yeah, we still have one class next week. Yeah, we do that next week. Okay, yeah, then see you tomorrow. Yeah.